Good afternoon. I'm Christina Gabardi, Program Manager here at the Linda Hall Library. Thank you for joining us today for How Do I Become a Geologist? This interactive program is specifically designed to give viewers the opportunity. Oh, I'm Christina Gabardi, Program Manager. Can you mute that? Apologies, one second. Geologist. This interactive program is okay. Okay, hopefully everyone can still hear me. This interactive program is specifically designed to give viewers the opportunity to ask questions to a professional. To ask your questions, type them in the Q&A chat box that you see at the bottom of your screen. If you're watching on YouTube, type your questions into the chat. We are pleased to be joined today by Dr. Bud Davis. He is a senior geologist at Drummond Carpenter. Dr. Davis, thank you so much for taking the time to speak with us today.
Thanks for having me. Glad to be here.
Yeah, of course. I will just throw it over to you so you can start sharing your presentation, and I will be back for the Q&A.
Great. Thank you.
Perfect.
How does that look? Are we good?
It looks good.
All right, great. So yeah, thank you for having me today. I'm Bud Davis. I'm going to talk to you about how I became a geologist and generally what geologists do and all the different fields and how you could potentially become a geologist. Um, Right now, I work for a civil and environmental engineering company that does private consulting called Drummond Carpenter. And I'll kind of touch on how I got there as my career path as we go on. Generally, my talk structure is going to kind of outline a little bit about what geologists do and then talk about my story, specifically how I became a geologist, because I think, there's some great examples. I've got good pictures, which hopefully lets you picture a little bit better what the steps look like and, what that process will actually be. And then at the end, I'll have, some suggestions and tips for those of you who might be interested in pursuing this as a career path. So geology is a really broad field, and geologists work in a lot of different disciplines, and there's not many geologists who have the exact same day-to-day job as other geologists. I kind of break it down into three main categories, being economic, environmental, and then I kind of group academic and government together, but they actually can look really different. Um, Economic, that's going to be geologists who are working in maybe the oil and gas industry or mining and mineral resources and working on economically identifying and extracting those resources. Then environmental, there's a lot on the remediation side. This is where I work. We're dealing a lot with groundwater and surface water, remediation, soils, climate. There's a lot of work that's being done there. Um, in a lot of different sectors, there's overlap with, all of these different fields. Then academic and government, academic, you're really going to be working on outstanding questions. There's a lot of focus on climate change and those impacts in both of them, hazards, earthquake hazards, those sorts of things, resource optimization, kind of some of the big picture problems that, water resources and even oil and gas and mine resources that might not be industry specific, but might be better served by, academic consortiums, things like that. So a lot of different things geologists do. Generally, they're related to the earth and earth processes. And at the end of the day, everything we eat, everything we use to power our homes and our vehicles all has to come through these earth processes, and geologists, help address those scientifically. So economic geology kind of touched on this, pretty broad field, but generally you're trying to identify the locations and volumes and quality of Earth resources, and then working with your knowledge that you have of those resources to figure out how you can extract them, cost effectively. So on the right, I've got some examples, some, basic stuff from the oil and gas industry. where you might look for oil and gas plays and use your geologic knowledge of the subsurface to identify where those are and help plan, deep wells, extract them. So that's just kind of an example of what this looks like on the right. But it's not just oil and gas, it's metals, it's coal, and basically anything that we're going to need to extract at an like economy scale, you're going to need geologists helping to manage, identify, and extract those resources. You're going to see a lot of structural geologists, geochemists, geophysicists, geostatisticians, and then also just basic sedimentary geologists, igneous and metamorphic geologists, a little bit more on the metal side, but a lot of different fields in there. I'll try and just kind of throw out some buzzwords there. But I wouldn't worry too much about that specialization right now. But just kind of some ideas to have for skills and titles that people might have. Some of the basics about working in economic geology, it's probably the best pay you can get as a geologist, but it's also going to have high lows that cycle with that industry. So there can be low job security. And I saw that, with a lot of my friends. Um, Oil and gas industry, wasn't doing so good about 7 years ago. A lot of people got laid off. And it can be pretty tough, people with young families. Um, but, people make 30-year careers working for the same company. And so it can absolutely be done. It's not one of those where if you go in oil and gas, you're absolutely going to lose your job. It's more of a roller coaster than I think, the other geology roles. And then, it can kind of be a messy industry. I think people can, have, altruistic problems with it, about extracting resources from the environment. But at the same time, I think once you start working in these industries, you see that it's not really as exploitative as you might think based on just like movies and things like that. Then there's environmental geology. Generally, these are going to have the goals to protect or remediate the environment. A lot of different techniques that go into that. A lot of focus groundwater, surface water resources, then your soils and contaminants that might be in there, and then climate change. To kind of group all of those together, so there'll be vulnerability assessments associated with climate change. Geochemistry, geostatistics again. You're going to have a lot of modeling here, a lot of field work, though, a lot of field assessments. Wetlands, I would put those under here, wetland scientists. A lot of different roles you can play in here. Probably too long didn't read here is moderate pay. Pretty good work-life balance, but it can vary firm to firm. There's definitely some firms that are gonna, ask well more of their environmental geologists than maybe an industry geologist. Industry geologists generally have pretty good 40-hour work weeks. Civil environmental engineering can go 50, go 60 plus at some firms. So it can be a little bit harder on that path, but a little more altruistic. Although at the end of the day, I think you can kind of see when you work in a lot of these fields that it does become a commodity almost in and of itself. And then academic geology and government geology, these are going to be kind of big picture macro environmental problems that you're going to be working on. On the academic side, you might be working more with research, and then on the government side, maybe policy. But it can also be you might get a little bit siloed here. When you start entry level, or you're working a lot of bureaucratic red tape kind of stuff, permitting that kind of thing. But it's going to be working in regulatory, climate, applied research, teaching. I'll put that under here. I think one reason a lot of people are attracted to, the academic side of geology is getting to teach others. It's a really cool field, and getting it to share it with people is the best. And you're going to see people from all specializations on the academic side. On the government, you'll probably see a little bit of the ones that were similar to the environmental. Too long didn't read there. You're gonna have good high altruism. If you're on the academic side, then you've got really good freedom, but you probably have some of the worst work-life balance. Not so much on the government. Generally, the pay is going to be a little bit lower on each of these. So there's trade-offs with all of them. And I kind of tried to rank them a little bit just to give you some perspective. So pay, economics going to be the best. Then I'd say environmental, then academia, then government. Work-life balance, government's probably the best, then economic, environmental, and then academia. Academia, it's just you've got research obligations, teaching obligations, you're trying to get funding. It can be pretty tough. You're advising other students, can be really hard, especially early career. And then kind of this freedom altruism. I think academia and government right at the top, and then environmental and economic. So a little bit of an inverse from the pay, but I think that's understandable. So traits to each, there's none that are perfect. I think, everybody can kind of find what fits them in geosciences. So a little bit of my story. I've been around, kind of touched on all of these different fields. So I got my bachelor's of science from the University of Florida. I was there 2008 to 2012, then went to the University of Texas and got a PhD there. That was paid for by ExxonMobil, and then did postdoctoral research at Columbia University for about, 18 months, almost 2 years. And then during my graduate school and then through my postdoc, I worked as a visiting scientist for ExxonMobil, and that was basically just being a consultant to them, private consultant. I'd come on a few times a year. They'd pay me, and we work on a few problems together that'd be just for them. And then since 2018, completely flipped. I've been working as a professional geologist doing environmental consulting, after I left postdoctoral research. So I've been doing that 6+ years now. During that time, I've also had a couple internships. 2010, during my bachelor's, I interned with an environmental engineering company called HDR. Then 2012, right after I finished my bachelor's, I worked as a summer intern for the USG, and I'll talk a little bit more about that experience. It was pretty cool. In 2013, before I started the visiting scientist post, they first brought me on as a summer intern for them. So, really jumped around, all the different sectors, academia, Columbia, government with the USGS, currently working environmental, spent years working with oil and gas industry, including an internship and then doing consulting for them. So gone really across the board, a lot of different experiences, but at the end of the day, I think there's a lot of similarities between them. So I would say undergrad geology, I still love geology, but undergrad geology is where I first fell in love. Um, so just a little bit about the undergraduate geology experience. You can get a Bachelor of Science or a Bachelor of Arts, so a BS or a BA. Generally, the BS is going to be a little bit more tailored for if you want to do, technical work going forward. BA is a little bit more tailored for, if you want to be like a science teacher or maybe then go get a master's of science. The BS is going to ask a little bit more from the hard science side in undergrad, and it's going to open up more doors for you. So if there's an option to pick between the two, and you think this is something you're really interested in, I would, strongly suggest going to the BS. I think it does open more doors. Courses, it is a hard science, but it's not crazy. You're going to take your calc, chem, and physics. Most programs want you to do at least through level 2 on those. So, you're not going wild. You're not going to do organic chemistry. Most of them are going to have you go into differential equations, but you are going to have to work. And a lot of these classes can be weed out classes at big schools. Like, for me at the University of Florida, classes are weed out classes for a lot of the med students. So they're pretty rigorous, but they're really good experiences. And you do actually lean on many of these principles in your work day to day. So they are important. Then you're going to get into your geology classes. You have lower level ones, which are generally going to be introduction to geology, maybe a local geology class for, University of Florida. It's your Florida geology class. You'll do a lot of field trips, and that's good for exposing you for kind of how to think. And, you might have a historical geology. So when people throw out different ages, you can kind of order them in your head. And then you'll get into a little bit of your upper level classes. These are things like mineralogy, where you're going to be looking through a microscope a lot and identifying minerals in hand samples and saying, this is this type of rock and it formed by this process. So being able to go from seeing something to thinking about a process is one of the keys that you need to establish there. Structural geology is kind of big picture. So, if you've seen the side of a cliff, and it looks like there's faults or folds, That's what's going on there. So structure is a lot about identifying those things and turning that similarly into a process and understanding what happened there. And then the capstone course for almost all undergraduates is called Field Camp, and it's amazing. Um, you're going to go out for, 2 to 4 weeks to a field site. You'll camp or stay at a lodge or something like that with the rest of your cohort, and you will spend that entire time going out to remote sites and using all of your different skills that you've learned throughout all of your undergraduate, and putting them into practice and making field maps and making field interpretations and being asked to decipher what happened here and tell it in a story and put together a report and put together a map series. And it's really great. Um, Overall, the whole undergraduate experience is very filled with lab work and field work, and you're going to be in a small cohort of probably 20 to 50 people for all of the same classes. So you're going to get really tight with these people. You're going to spend, evenings in the microscope lab where none of you are quite good at looking at rocks under a microscope yet, and it's really tough, or you're really trying to all decipher this random rock that the professor left in there that's on the quiz, and you're all looking at it and trying to do all the different tests to figure out what it is. Or you're going to go camping where you're learning basic structural or igneous metamorphic principles, and you're going to be around campsites, and you're going to spend a lot of time with these people and get really close. And I think that camaraderie is really something that's unique to geology and also just makes it a lot of fun during undergrad. If you like being outside, if you like being challenged to decipher puzzles, particularly outdoor puzzles, or thinking about processes based on, you see something, you use deductive reasoning to figure process happened here, almost like a detective, then, geology is really good for you. And there's great opportunity in undergraduate to work in professors' research labs and get paid for it and get an undergraduate thesis put together that will ultimately give you a really strong master's thesis or master's or graduate school opportunities. So it's a really good field to be in, particularly in undergrad. I think I've got some photos to share. So yeah, this is from, 12 years plus years ago, probably 14 years ago now. Um, just kind of what it looks like. This is our Florida geology class, all of us, and we'd go out to, areas. We don't have a lot of great roadside geology in Florida, so we do these, overnight weekend trips up to Georgia and North Carolina and the Appalachians, and look at these rocks and look at these outcrops, and we'd get instruction in the field. You'll have things like notebooks, and you'll have your big clipboards, and you're asked to make cross sections and notes and drawings of those, and you'll listen to a lecture and hold the rocks and see them, out in nature, oftentimes just along the roadside. It's pretty cool. And then, you camp at night and you play cards, and these are people that you're spending 40 plus hours a week with. And so you get to be really close because you're doing it, not just for 1 year, but, oftentimes 3 or 4 years. So these get to be really close friends, and it's a pretty special experience. I did my undergrad thesis working in a paleomagnetism lab. So paleomagnetism is pretty cool. The Earth's field flips polarities every so often, and you can take rocks and you put them in the ovens on the left. You put them in there, and you can evaporize them sequentially and then measure their magnetism. This whole room is a big Faraday cage, so there's no magnetic field in there. And they really isolate any electronics. So no cell phones, nothing in there. And you can measure the magnetism of these little rock samples that you cooked in the oven to figure out what the Earth's field was at the time that this rock was formed. And then if you know when this rock was formed, you can use that to kind of deduce where this rock was when it was formed. And we can use this information to figure out where different geologic plates were back in time. So I got to do that in undergrad and get paid to do it and get a thesis built out of it. But I spent a lot of time, in these labs. Oh, you can see the little samples under the oven on the picture on the left. They're really tiny. They're, just like a square centimeter, basically. Um, and just working with hundreds of these little samples and putting them in the oven and then measuring them in the magnetometer, which is on the right. And it was pretty cool. It was actually me getting to do the science, and it's a lot of really repetitive grunt work, but there's something kind of peaceful about doing a couple hours of lab work where you turn your brain off and you can't even have a phone in there, you can't have music or anything. So your mind can almost go into this like meditative place. So that was pretty interesting. It was a good experience though. I enjoyed it. Oh, this is our field camp. So, we would go out to Taos, New Mexico. This is the lodge we would stay at. We'd stay up in the Taos Ski Valley because it was the summer, it was their off season. So nobody else was there except, other geology field camps. And we'd drive across the country in these white vans and we'd go into this ski lodge and all stay there up in the valley. And then we'd go out and you can see I got my rock hammer there on my shorts. And you'd go out to these sites and you'd get asked to map it. And I got my field notebook in my hand and you're walking around and putting all these principles that you learned into action. And so you're mapping things. This is on the left, this is a stratigraphic section of the basalts that are out there from the Rio Grande Rift. And one of the assignments is, how thick are the basalts there? And so you have to use these principles to measure the thickness of these layers. And so that's a pretty cool one. You work your way up this hole from the river up to the top of these cliffs to try and figure out how thick all the different layers are. On the right, this is another site we did our mapping at, and you can see kind of some of the different layers. There's some, more white rocks up here, red rocks down here, and then some kind of almost dusty looking sands down here. Those are all just really big, important layers that are out there in the West. And this is a place we did more mapping called Ghost Ranch. It's a pretty famous little Western site. You'll see it pop up in movies. We were out there around the time they shot Cowboys and Aliens. If you've ever seen the old movie Red Dawn, it pops up pretty prominently, some of the scenes. So it's like you see it and you're like, hey, I know that. That's Battleship Rock. I remember mapping that by hand. So it's pretty cool to go visit some of these, famous Western sites. This is kind of what it looks like. You literally get all your gear and you have probably one partner that you're mapping with so that, you can work together. Some things take more than one person. You'll have these items called Jacob staffs. They help you, get at how thick different things are. And you'll have a compass. So you measure things like the strike and the dip. And you can triangulate your position. We didn't use GPS. Now GPS is a bit more common. But we actually had to triangulate it with a compass, which was pretty cool when we made these maps. But you just hike out there and you get asked to map these really amazing world-class geologic sites. And then, they mix it in. Ours ends up going 6 or 8 weeks because you mix it in and you take trips to national parks. So this is, Arches National Park. And I got to visit that on a class, which was really cool. It's a beautiful place. This is at Angel Landing, which is a really scary hike, and I don't like heights, but it's totally worth doing if you ever have the opportunity. It's beautiful up there. Just some more pictures from the field. Just these are amazing world-class, cross-bedded dunes. American West used to be filled with these dunes, and you can go out there and actually see them. This is me and another dude for scale. They're huge. This is us out on a similar exercise. I think this day I almost got bit by a rattlesnake, and it's scary, but also you learn a lot about yourself. You get tested when you're out there hiking around 10 hours a day. But it's also really fun. It's challenging. It's stressful. You're doing it with people that, are almost like family at that point. So it's really cool. All right, so then once you do field camp, you either graduate the next year or the year after, but you're pretty much done. And after I finished undergrad, I ended up before I started grad school, I did a summer internship with the USGS. And this was really neat. I was out in Lakewood, Colorado, and I got to work on a sediment core that they collected out by Great Sand Dunes National Park. And this project was a pretty neat one. So there's a big valley near Great Sand Dunes. And there's a lot of farms there. It's pretty arid, and the farms rely on a thick layer of clay in the subsurface to act as what's called an oxide, but basically it's what gives you the groundwater as a unit underneath. And they wanted to know where the aquifer was and really how did it form. So they collected this core and they collected some aeromagnetic data and they were able to map this blue clay layer throughout the valley. And then I worked on identifying the layers on the core themselves, and then I did some of that PMAG, paleomag on it as well, so we could, date the core because we can tie recent magnetic reversals really well to the geomagnetic timescale and figure out how old things are. And so we were able to show that, when this lake used to fill the valley, it filled it with clay, lakes deposit clay, um, filled the valley, and then eventually it broke out of the valley. And this is like the old ancestral Rio Grande. And so the timing on when the clay layer goes to sand is the timing of when the lake broke out of the valley and the Rio Grande started going south from this position. So it was really cool to be able to work on a novel research project like that as an intern. And then, I got to present it at the Geological Society of America conference as a paper. And ultimately, we turned it into a paper. So it was really cool to, get to do novel research like this, just so young, and have results where it's, man, I'm the first person who knows when this Rio Grande, this Lake Alamosa broke out, and the Rio Grande started heading south from this part of Colorado. So that's really neat. You don't get those types of experiences in every field, and I feel like geology is really good at giving you those experiences and particularly giving them to you when you're young. Grad school. This is me giving a talk at the American Geophysical Union. That's the really big conference every year. It's in San Francisco, and this room was really full. This is me taking a picture before it because I was nervous. But grad school. So generally, there's good opportunities whether you're interested in master's or PhD. Both of them, thumbs up, going to open doors for you either way. You don't have to feel like it's PhD or bust. Generally, PhD, you're going to need it for academia, but otherwise, master's and PhD, they're both going to open doors. PhD might get you a little bit more in environmental and economic, but it's not like it's the only option. Both of them have a lot of similarities. You're going to have something you're going to focus on, a specific topic that you're going to specialize in. You're going to take advanced coursework, and you're going to do original thesis or research for both. So that's a research topic, sometimes guided by your advisor. Some of it you're going to have a lot of input on, and you're going to take it from its infancy, usually in data collection, all the way to publication for a master's or for a PhD publications. And both of them will involve some kind of defense where you'll have a committee that is formed. You'll have your thesis committee, and they will investigate the research you did and ask you questions. And you'll need to defend both your thesis, and you'll have a qualifying exam if you're in there for a PhD where you'll have to defend your broad geologic knowledge as well. Some of the benefits is getting specialized. If you can get specialized in something that's really cutting edge or important, you are very valuable. So specializations in and of itself can be extremely valuable if it's the right thing. Technical skills, you're going to get great technical skills in grad school for geology. Data analysis, you'll have specialized skills for your area of research, but generally you're going to get broad data collection, data analysis, scientific method, best principles, technical writing. Those are generally the things that I think people come out of this with that are broadly applicable in addition to their specialization. The network as well. I think that's hard to undersell how important having a network built out through grad school is. And ultimately, all these are important because it's going to give you more pay and more freedom versus just a bachelor degree. So this is what I did for my graduate school thesis. I got a PhD in geophysics. So I worked on understanding how continents rifted apart. And, I did that both using geophysical methods and data, as well as doing numerical models of how continents rift. So on the left is a figure from one of my publications in my thesis. This is the margin I chose mainly to focus on, which is the East Antarctic margin. So this is the part of Antarctica that's between Africa and Australia. on the southern part of the Indian Ocean. Really cool margin. A lot of my work was looking at the seismic, magnetic, and gravity data in there and trying to figure out what type of crust it was. And that matters in Antarctica because the Antarctica is a shared international territory, but there are generally claims made to who owns different parts of Antarctica, and your economic zones are impacted by where the continental crust limit is. And the Australians, who have major stakes in this part of Antarctica, were contending that the continental crust went out several hundred kilometers into the oceanic domain. And I looked at this geophysical data and it's like, no, I think we need to scale these back significantly. And so I offered up an alternative explanation, which I think we ended up seeing is pretty well substantiated, not just here, but also off the eastern coast of the United States, where the limit of continental crust might be significantly more inboard than people were previously thinking, and there's a lot more oceanic crust. So a lot of geophysical observations went into that. And then on the right, this is just a video of this numerical modeling that I built out. This is some Fortran 2D numerical modeling we put together, looking at continental deformation and mantle deformation, and ultimately lithospheric melting or asthenospheric melting. So this process, this melting process, is really the novel thing that I coded up. The continental breakup code existed beforehand, but it didn't have this melting component. And that's really critical because this actual melting is what gives us oceanic crust. And so understanding the timing between when do the continents break up and when does oceanic crust start forming is really important. And it's especially important to oil and gas companies because you can get oil and gas plays on top of continental crust. It is extremely difficult to get oil and gas plays on top of oceanic crust. Just the thermal profiles are so different that you really need to know where this limit of continental crust is to understand how valuable a potential resource is. So when I worked with Exxon, I did a lot of work. Let's see if I can go forward. So this is some more modeling I did. I did plate reconstructions of the Indian Ocean as well. So this is taking similar magnetic principles of reversals, but looking at them in the magnetic and gravity data, the seafloor, to try and figure out when continental breakup actually occurred down here. And so we build out these plate models. Companies like Exxon care because they're bidding on an oil and gas play down here in South Africa, and they want to know, hey, it looks pretty good on the seismic, but we can't tell if this is oceanic or this is continental, directly from this 2D seismic. It's kind of in this in-between realm based on all the geophysical properties. What about processes? Can we think about processes to understand that a little bit better? So I ended up, working with them on that. And, all three of these were three different publications. And then it was just chapters 1, 2, 3 in my PhD. This is me after graduation with my wife. And then this is me on the right. And it's really cool. Like, I didn't even know this, but we went to the Smithsonian and all of a sudden I saw our group's research on the wall of the Smithsonian. So that was amazing to see. This is from the UTIG Plates Project. That's at the University of Texas Institute of Geophysics. So yeah, it was really cool to get to contribute to just broad stuff like that. That was neat. During grad school, I had all sorts of cool opportunities to travel as well. This is me with the world's northernmost statue of Vladimir Lenin up in a town called an abandoned Russian mining town called Pyramiden up in the Arctic Circle on the island of Svalbard. So I've gotten to go to the Arctic Circle, and then this is me down on South Georgia Island down near Antarctica on another research cruise. So the one on the left was paid for by Statoil, which is the Norwegian state oil company. And then this one on the right, this was an NSF research cruise. And so I got to see penguins. So I got to go to both poles during grad school. So, not many fields where you get that type of opportunity. For Antarctica, we were on a research boat. This is the Nathaniel Palmer. It's an NSF icebreaker that they use for research at the poles. So we were on this for about 30 days. This is the island of South Georgia there. We went there right when their summer was starting, and you'd take these little Zodiac boats from the side, and we were installing GPS stations on the island itself, as well as collecting geophysical data offshore to try and figure out what the heck, why is South Georgia there? What's it made of? What's going on? What plate is it on? It's a pretty random little island. Doesn't make a ton of sense. This is where Shackleton was rescued. Um, this is where he got stuck. His boat got stuck in the ice in Antarctica. They took one of their little essentially life rafts, sailed it, across a lot of the Southern Ocean, reached South Georgia, and got rescued by a whaling station there. So we could go there. It was pretty neat. Uh, this is one of the bases, the year-round bases that are maintained there. This one's called Bird Island. And so, we'd have a lot, we didn't have we had pretty good food on board, but, we got provisioned at this point, a couple weeks ago, but we show up at this base with a pallet of limes and avocados and lettuce and bring it to these researchers. And they hadn't seen anybody since the previous summer. We were the first boat there. And so we brought ashore all these fresh fruits and veggies, and they were our best friends. And so they helped us out a lot. And we hiked up here. It was like a mile hike, but it was pretty brutal, in the sleet, in this stream. Put in a GPS station up here. This is the we'd outfit out. We had solar panels, the GPS stations themselves, and then these humongous little, these not little, giant car batteries that we carry on our back. And so get on the boat, take the boat to shore, unload it, hike it, and install it. So that was pretty cool. This is what it actually looks like when you're collecting geophysical data on the boat. This is the seismic streamer, where you're shooting seismic. We're collecting bathymetry there, side scan, sonar, all sorts of stuff, gravity and magnetics. Just a really cool experience to get to be out there. Mainly, I'm a marine geophysicist, as well as a numerical modeler by training. Did a lot more marine geophysics. This is us collecting a piston core here. This is us working on a seismic streamer. This is in the Gulf of Mexico, offshore the Brazos River. This is actually a small little boat called the Petty that we took up the river. And you go out and you collect the data, and then you come back and you've got all the workstations and snacks set up on the dining room table, and you process the data. So a little bit different than working on the big NSF boats, but kind of the same principle. And it's similar to undergrad. You get really close with these people, doing this type of work. Did some field work as well, not just geophysics. This is out at Anza Borrego National Park. I went out there a bunch. This is where my grad school roommate's field area was. He was working on these deposits on the right. These are called turbidites. These are the offshore channels where oil and gas usually ends up. So it's really important for people to understand, those who are looking for oil and gas, to figure out exactly what they look like for these units they're playing into. This is a really cool fold out there. You can see it's bigger than these, giant SUVs we have. So then I finished up grad school, went and did a postdoc at Columbia, and it was pretty similar research to what I did on the East Antarctic margin. This was mainly looking at the magnetics of the North American margin offshore North Carolina. Similar seismic grav mag. They collected it on boats offshore there, and we were trying to figure out what's going on. It was a good experience. I think the postdoc was really hard on me. The purposes of postdoc are you're building out your research, you're building out your network, and you're trying to find an assistant or associate professor position and firm up your kind of funding network, getting some proposal into your belt. And so I really liked the research side. I liked the networking side. And I was really miserable trying to do those at the same time with applying for jobs and writing proposals. And, I was just stressed all the time. I really felt like I could never stop working. I'd get home, I work all day on my research, get home, have to work on job applications, have to work on proposals. So after about 18 months of that, I was pretty burnt out. And my wife and I started talking about what we wanted to do. And we wanted to move back to Florida and get with family. So I started talking to this guy, Chad Drummond. He's in the middle here. And he was like, hey, you're a smart dude. Modeling. I do a lot of modeling, but it's in environmental consulting. I can teach you our models and turn you into an environmental consultant. So I completely switched 2018, made a career jump, no longer working with oil and gas companies. Now I'm working on a lot more environmental remediation. still do modeling, same modeling principles that I had when I was working on continental rifting, but now I'm working on surface water, groundwater modeling, radionuclides. That's probably one of our biggest areas in contaminant transports. I do a ton of statistics, data analysis, and machine learning, and I've gotten to build out our geophysics practice. So I came on in 2018 as employee number 6. This is at our corporate retreat back in 2018 in Michigan. We are about to have our corporate retreat this year. I leave for that tomorrow, and now we're up to 30 people. So it's been really cool to grow the company. The big clients that I work with are the Department of Energy and NASA, but then just overall, our companies work with a lot of state, local, county level municipalities. And I think that's fairly typical. Environmental consulting, you're going to have a wide array of clients from private to public. We're service disabled veterans, so we mainly focus on public sector because we usually get a little bit more points when we go after bids. So we're service disabled veteran owned small business. So when you bid on a project, you respond with a proposal and it gets scored, and we get usually just like 1 or 2 extra bonus points for having that classification. Working as an environmental consultant, as a geologist, a lot of states you need licensure. So I'm a professional geologist in Florida, Tennessee, Pennsylvania, and Arizona. Not all states require professional licensure, but a lot of them do. And it just helps open up doors. It also helps you charge more, which lets you get paid more. Some examples from our projects. So this was on the left is from one of our clients who they've been dealing with a lot of flooding, historic flooding. And so we're looking at best management practices, or BMPs, to help alleviate that. So we build out numerical models of what the surface water is doing, design, existing conditions models, and then we make a design to alleviate the issue, run those models and see how effective it is, and then use those models to get it permitted and implemented. So that's pretty cool to be able to help. This is a small municipality that has an airport that's just getting inundated by floods. So helping them out with that. And then, we do things like this is Wekiva Springs is a big springs here outside of Orlando. And, we want to protect its water quality. It's impaired for nitrogen. And so we built out a 3D geologic model of the subsurface. We modeled the groundwater, and we took a bunch of water quality as well, did some isotope modeling from the water quality data itself. And we've been able to understand that septic and fertilizer are having major impacts on negative impacts on Wekiva Springs. And because of this information, the county's been able to make informed decisions about what neighborhoods they need to disconnect from septic systems and connect to sewer systems, and where do they need to implement fertilizer bans, both in space and time. So that's pretty cool. This is another one of these big groundwater modeling projects. This is trying to look for aquifer recharge opportunities. So we build out these big 2D models, and we do a bunch of modeling for it, how system drains, and we look at areas which might be good for implementing aquifer recharge or might be bad for it. These are shallow water table conditions, so not great to try and implement aquifer recharge there. But you can get these areas over here where you're connected to a drainage system, but the water table is deep, so you have a lot of potential to recharge the aquifer there. So that's pretty neat. This is one of my big clients. This is White Sands Test Facility. It's located outside of Las Cruces, New Mexico. They've been testing rockets there since the Apollo program. As a result of some of those rocket tests, they've got environmental contamination. When we started talking to them, they didn't have any idea what their subsurface looked like. They really didn't have their plumes well quantified. And they had about 200 wells they drilled, and they had a pretty ineffective treatment system. And since then, we've been able to do a lot of geophysical data integration, lithologic integration, and build out what we call a conceptual site model, so they can understand what the subsurface looks like in terms of its geology, as well as quantify their plumes and how these plumes are changing through time, so they can target their treatment strategies a lot better. Helps with regulators. It's just real to take clients and their understanding forward and get to help out with a problem like that. Another big client, this is Oak Ridge National Lab, so Oak Ridge, Tennessee. This is one of the big, it's a Manhattan era Department of Energy site that, they need to dispose of a lot of existing buildings that are on this site that are contain, hazardous radioactive waste. And so they need to build a landfill for it. And so we've done a ton of radionuclide and as well as hydrogeologic modeling for how this landfill would function and make sure it meets, regulatory, um, regulations, federal, state, local regulations. So we have to be able to prove that with models. And so we help build that out. And this is a little image from some software we use called ResRad. And it's all the different pathways which you might be exposed to radiation in a hypothetical future scenario that we develop. This is another one for the DOE. This is a site called LBAR. This is what it used to look like on the left. It's a former uranium mine and milling facility. They mine the uranium there and at another site nearby called the Jack Pile Mine, which was one of the biggest mines in the world, back when it functioned. And they have these tailings as part of this uranium ore processing step. They end up with these tailings and these slurries, and they closed the facility and they put it all into what we would call a disposal cell. And they started having some problems with it and asked us to do a geophysical investigation to figure out what was going on. And ultimately, we were able to show that, it's probably just some localized erosion and it's not some massive issue. But it was pretty cool. This is some electromagnetic data we collected on the site. These are resistivity data. So this is the electromagnetic data. We weren't allowed to drive on the site due to some of the site conditions we were worried about, so we had to walk it. We walked like 110 miles, pretty key of this data here. So walked it across the site. This is us collecting resistivity data. Car batteries, nothing like hauling around car batteries. I've done it a lot. But just a beautiful part of the country, and collected this data. Basically shows all the waste is staying where it needs to. The cap's performing like it needs to. You can probably patch up some of the things you're worried about with some more sand and clay, which is a good thing to be able to prove out for a client. All right, so that's my story. So some tips and tricks. So I would recommend, number one, just explore geology a little bit. There's a lot of benefits. You're never going to look at nature the same way again. You can travel anywhere in the world and look at the side of the road and, feel really compelled about what you're looking at. You'll go to the beach and the beach won't look the same. You'll go to the mountains won't look the same. You'll be next to a river and you'll notice processes that you've never seen before. And you can do that all over the world. I always like to tell people it's like solving 4D puzzles. There's 3D space and then there's 4D time and there's these processes. And I kind of compared it to being a detective earlier. But you're always asked to, solve them, whether you're working in economic, environmental, academia, government. There's a lot of places where you can find role. No two geologists are the same. I met a lot of different people. There's a lot of great camaraderie travel. So how, if you are interested, do you get into it? I would recommend in undergrad, take a Geology 101 class. That's what I did. I had no idea I wanted to be a geologist. Took a Geology 101 class, really liked my TA, really liked what I was learning, and switched. So if you take Geology 101 class and you like it, talk to an undergrad advisor. There's going to be a geology department. There will be an undergraduate advisor in that department who will tell you more about the classes and how to switch or become a geology major. And also do cool research. Talk to professors. Do research with them. You'll get paid to do it. It'll be really interesting and it'll teach you a lot. All right, and then some of my advice I never get tired of sharing is to ask dumb questions. And this has been something I've felt strongly about from undergraduate to graduate school to my career today. Dumb questions are amazing because they're often not dumb questions, or if they are, you learn a lot about how people respond to dumb questions because you want to work with people who are receptive to dumb questions. If you ask a dumb question and somebody is mean to you, then you learn that you don't want to work with them. You learn that they're a bad teacher, or they're a bad boss, or they're a bad coworker, or they're a bad client. You learn a lot just asking questions. But usually, when you ask questions, it helps you understand so that you can contribute, makes you feel like makes you a better team member. And often it helps somebody else who had the same question but wasn't willing to speak it also understand. And then I've also found there is this larger than you would expect percent of the time that your dumb question is not actually a dumb question. It's a really good question. and you need to be thinking about it, and the other people in the room need to be thinking about it, and it moves things forward, prompting research or prompting an investigation or getting an answer from somebody else that you really needed. So ask dumb questions. That's some of my favorite advice to give to people. I wish I had done it my whole life. Right. And then let's see, do I have one more? Yeah, I think that's it. So I'm happy to answer any questions. Feel free to reach out if you want to reach out to me personally. It's just bdavis@drummondcarpenter.com, and I'm happy to talk to you. So thank you.
All right. Yeah. Thank you, Dr. Davis. I love the tips at the end and amazing to find your Smithsonian or your research at the Smithsonian. That's insanely cool. So yeah, let's start taking questions. And as a reminder, if anyone has any questions, type it in the Q&A chat box. If you're on YouTube, type it in the chat section. Um, let's see here. Any advice on selecting an undergrad program? Do all colleges basically offer the same type of program for a degree?
So not every college offers a geology Bachelor of Science. It's something I would, if you are really interested in it, I would check to make sure they offer it as a major as well. Um, and it's kind of hit or miss where it is. There's big schools without it, but then there's also small schools with it. So it's just something you kind of have to check on a school by school basis. Um, and there are great geology programs at small schools with low US World and News rankings, and there are bad geology programs at awesome schools with high US World and News rankings. So, it's tough to kind of use anything like that, but you can email the undergrad advisor and probably like look at the college, make sure they have it as a major, email the undergrad advisor and kind of figure out a little bit what the vibes are. But I really don't think you can go wrong in an undergrad at all.
And sticking on the undergrad topic, is it possible to become to specialize with an undergrad degree?
Not really.
Okay.
Undergrad is pretty broad. You might get a little bit of specialization, if you do a thesis topic, you'll get a little bit more, but not enough where it's gonna, prevent you from going one career path versus another.
Gotcha. And still on the topic of specialization, are there specializations within the field of geology that you foresee being especially important and in demand in the next couple decades?
Hmm. Pretty good one. Um, I think getting the geostatistics stuff is pretty new, and especially the ones that are leveraging techniques like machine learning. Um, that's pretty novel. Um, using taking geology techniques like that we've had in like aeromagnetic data that we used to collect by helicopter to be really expensive. Now you can put it on a drone and it's really cheap. And now we have LiDAR data that's extremely cheap to collect. The data sets are getting bigger, and geology doesn't have as much experience handling that. So I think geostatistics and remote sensing are two big ones that are blowing up right now. And then otherwise, I think a lot of the water resource stuff is particularly important now, and going forward, it's going to be more and more important.
Yeah, definitely. So we have another question. Do you think it's possible to get a good career with just a bachelor's, or is getting a master's just the best option for that field?
Now, you can have a career with just a bachelor's, but it's going to be harder. Oil and gas, you're going to spend more time on the drill site than in the office making decisions. And it's just going to make it harder for you to step up and get paid more. So that's like industry side. Environmental side, you're going to spend significantly more time just, as the field guy going out and collecting the sample from the landfill or collecting the, wetlands data. You're going to spend a lot more time there before you get trusted to actually handle like the project management stuff. Um, or, on the government side, you might get stuck more in the lab or the permitting office. Um, versus if you can get the master's, it's going to open up significantly more doors for oil and gas industry. That master's is almost guaranteed if you want to work at a higher level there. Environmental, it's going to get you more on the project management side and the planning. You're still going to have some field work component probably, but you're going to start off not necessarily being the field guy, and people are going to kind of look at you a little different, and you'll just have a little bit better problem solving skills. Um, and then government, masters, it's similar to environmental where you might come in more as a project manager almost level out of the masters, but it's almost just trading time. So rather, you're going to get paid to go to grad school for geology degrees. I don't know if I really hit that hard enough, but grad school should be paid for. You will not have to pay to go to grad school um, because these guys are doing research topics where they need graduate assistants, research assistants, or your university needs teaching assistants. So you'll get a stipend and your courses will be covered as well. So really the benefits of going to grad school, I think, outweigh the cons because the time trade-off, um, it's going to pay off eventually, and you're not going to go into debt doing it. So
Yeah, that makes sense. And so you got into geology in your undergrad. What would you recommend if you were already sort of interested in that in high school? What type of classes do you need to just hit if you were already interested?
you're just going to make you're going to make your college a little bit easier if you can take the AP Chem Calc Physics. Like, if you can knock those out, then you're not doing the prereqs. Um, you know, you're not going to probably get a good geology course in high school, but if I think there's like an AP environmental science class. I think that type of stuff is helpful. Yeah.
Can imagine that would get you really prepared. So you showed a little bit about what it's like, what you're doing at Drummond Carpenter. Could you talk a little bit more about the breakdown of that? Like, are you traveling all the time? Are you in an office setting often? What does that look like?
I think I probably travel. It's probably 3 or 4 days every 2 months. Um, and that can just be national travel, conferences, client meetings, things like that. I think, COVID has made virtual meetings great. We don't have nearly as many in-person meetings, but we do usually our big clients, Oak Ridge and White Sands, we like to visit once a year. But I'm in the office most days, work from home. I think hybrid is pretty common as well.
Great. And someone asked, just curious about your site visits for new clients. How do you navigate possible health or safety risks?
Yeah, they're pretty regulated. You will have to develop and submit usually a formal health and safety plan before you go out to sites. Um, and you will have usually daily safety briefings. And if you have safety incidences, then you will recap those. There's big safety culture in civil engineering as well as oil and gas industry. Safety culture, you'll kind of learn a little bit more about that, but it's great. It takes a lot of the stress off, going out to these DOE nuclear waste facilities. I'll get more of a dose from flying in a plane than I will at the facility themselves. Sometimes you get a little Geiger counter, put a little dosimeter, they'll put it on your clothes just so you have it so you feel good. Yeah, it's cool.
Yeah, I was definitely surprised to just see how much physicality was involved with all of the hiking and unexpected things of that sort. So you talked a little bit about working with a cohort or within groups during your education. Um, are you usually working in a team in your field, and how big is that team?
Usually we're on a team, and usually I would say 3 or 4 people. Yeah, is a
Okay.
typical project. There'll be 3 or 4 people involved.
Okay, pretty tight team. And you showed video examples of the modeling that you've done. Is there some sort of software or technology that an aspiring geologist should be aware of or be familiarizing themselves with?
I don't think so. It changes pretty quick. I think basic programming skills, I like Python a lot. People use a lot of R. Those two are great, but basic programming skills set you up pretty well for good modeling skills. Um, and that constantly changes. So
And we have a question regarding job interviews. Could you talk about the process of job interviews? Is there anything particularly specific to that?
it varies. It does, networking comes in a lot to it, and then just being able to talk about examples of problem solving. Also, my 2-year-old's about to walk in, so it might get crazy in here.
Oh
But yeah,
boy,
but
grand
just talking
finale.
talking about like how you have solved difficult problems is always a good skill to have, I think, for job interviews.
Gotcha. And yeah, that about takes us to the hour. So, thank you so much, Bud, for the awesome presentation and for answering everyone's questions. Oh boy, let's.
You come say hi. You say hi. Hi.
Hello, hi. What's your name?
Kane. This is
What is
Kane.
that? Oh, Kane. Hi, Kane.
Hi, I was talking about being a geologist. What'd you do today? Yeah, we're just thrilled. Thank you so much for having me.
Oh, yeah, yeah. Thank you so much for answering everyone's questions, and thank you all for tuning in today. For more information about Linda Hall Library, visit lindahall.org, where I also encourage you to sign up for our newsletter. And for the parents and teachers tuning in today, I hope that you consider supporting the library through the Linda Hall Library Foundation. Your contributions make all of this possible and freely available. So thank you, and enjoy the rest of your day.
Thank you. Bye.
Bye.
Undo it.